Okay, continuing Unit 1. Now we're going to talk about two-dimensional kinematics. Again, kinematics is the study of motion, and two-dimensional things are now moving left, right, but they're also moving up and down. They're moving in two dimensions. So examples of this are a football being thrown through the air, or a tennis ball flying off of a tennis racket, maybe even a diver jumping off of a diving board. So we call this projectile motion, two-dimensional motion. The most important thing to remember about projectile motion is that in the horizontal direction, the velocity is constant. Gravity pulls us down, so gravity in no way affects our horizontal motion. But in the vertical velocity, we have an acceleration of gravity. Okay, always pointed down. We typically are going to ignore air resistance. The trajectory is the path that it follows. This is a trajectory. The maximum height occurs halfway through, assuming that we're on level ground. Again, we have nice symmetry here. And the acceleration is always pointing down 9.8 meters per second squared, or usually we'll just use 10 meters per second squared when we're solving problems. Let's take a look at some graphs. So here we have some graphs, and we want to in our minds be able to separate out the horizontal motion and the vertical motion. Okay, so this is what I was mentioning up here, is that the horizontal motion is constant, but the vertical motion is accelerated. So we want to be able to kind of split this up in our minds. Horizontal motion has a constant velocity. So the slope of the position time graph needs to be constant, because the slope tells me the velocity. The velocity graph needs to be constant, because we only have one velocity. I'll call it Vx, x standing for horizontal. And since we're moving with constant motion, the acceleration is 0. But in the vertical dimension, it's not constant because gravity is acting vertically. So I'm actually going to start with the acceleration graph. Gravity is always accelerating us down, meaning negative. And I can even put a value in here, approximately 10 meters per second squared. So at every point in the motion here, gravity has an acceleration of 10 meters per second squared. Now, when I throw something in projectile motion, at first it's moving upwards, and then briefly the vertical motion is 0 at its highest point. Then on the way down, it's negative. And so the graph is going to look like this. Okay, at first, it's got a positive velocity. For just a second, the vertical velocity is 0. That's at the highest point. And then on its way down, it has a negative velocity. The position time graph is a parabola. Okay. Give these next two problems a try. Go ahead and pause the video now, try the problems, and then play the video after you've tried them. Okay, go ahead and pause now. So you should have tried both of these problems. First one, a ball is thrown and follows the parabolic path shown above. Air friction is negligible. Point Q is the highest point on the path. Points P and R at the same height above ground. How do the speeds of the ball at the 3 points compare? Well, right away, I know for a couple of reasons that P and R are going to have the same speed because of symmetry. Okay, when an object is moving up, when it gets back to its original height, it has the same speed, just because of the symmetry. Also because of conservation of energy. Okay, so P and R have to have the same speed. Velocity of P has to equal the velocity of R. So this could be a choice E. Choice D could be a choice. And I can eliminate all the others. Okay. And as the ball's moving up, its vertical velocity is getting closer and closer to 0. Okay. So up here it has 0 vertical velocity, which means that it's lost some velocity as it goes from P to Q. So the velocity at P is greater than the velocity at Q. So choice D. Which of the following diagrams best shows the direction of acceleration of the ball at point P? This is what we talked about earlier. The acceleration of gravity is always pointed down towards the center of the Earth. Okay? It doesn't matter which way the object is moving, the acceleration of gravity is always down. When we get a projectile motion problem, what we do is we separate it into 2 problems. And we separate it into 1 for each dimension. 1 for the horizontal, 1 for the vertical. And you'll see an example soon, but it's important to remember that time is the same for the horizontal and the vertical. In the horizontal direction, we have constant motion. So we use the constant motion equation. In the vertical direction, we have acceleration, we have free fall, so we use our 3-star equations. Let's take a look at an example. Go ahead and try this problem. Pause the video. Start the video after you've given this a try. Okay, you should have attempted this problem. A rock with mass m is thrown horizontally with speed v0 from a cliff of height h. How long is the rock in the air? That's time. And how far is the landing position from the base of the cliff? So this rock is going to, as soon as it leaves the edge, it's going to start falling. It's going to start falling. And the shape of the path makes a nice parabola. This distance right here, from the edge of the cliff to where it lands, is the horizontal displacement, and the vertical displacement is h. So we're separating this into 2 problems, 1 for the vertical, 1 for the horizontal. I'm going to start filling in variables where I can, but first I'm going to circle my unknowns that I'm looking for. I want to know the time. Remember, that's the same for both. And I also want to know how far is the landing position. I would like to know delta x. That's what I'm looking for. Okay, now I'm going to start putting things into the problem. But first I'm going to define positive is to the right, positive is to the right, negative is to the left, positive is down, negative is up. Okay. My displacement is going downwards, h. I'm calling down positive, so this is going to be a positive h. My initial velocity is v0, and this velocity is only in the horizontal direction. v0. I don't have any velocity pointed up or down at the beginning, so the initial vertical velocity is 0. I need to know one more thing. Okay, we mentioned this in the last review. I can't solve a kinematics problem unless I know one more thing. And that one more thing is that we're in free fall here. So the acceleration is g, 9.8 meter per second squared. I'm not going to plug in that number because this is a variable problem. No numbers, no units. Okay, I have three things. I want to find time. I'm going to use my second star equation, which is displacement equals v naught t plus 1/2 at squared. First, right away, I'm going to cancel out this term because the initial velocity is 0. And I'm going to solve for time. Time equals the square root of 2 times the displacement all over a. Plugging in my variables, time is the square root of 2h over g. Okay, now I know the time. Time is the square root 2h over g, square root 2h over g. So that's the first part. Now I want to know how far does it land. When I'm doing the horizontal motion, when I'm solving for the horizontal motion, I only use constant motion. Displacement equals velocity horizontally times time. Displacement equals v naught times the square root of 2h over g. And I'll leave it like that. This is a variable problem. Let's move on. Here's another projectile motion problem. Two-dimensional. The object's moving both up, down, right, and left. Go ahead and try this problem. Give this an attempt. Pause the video and play when you're finished. Okay, you should have attempted this problem. A broken pipe sends a jet of water shooting from the ground at an angle of 30 degrees from the horizontal. The water reaches a maximum height of 10 meters above the ground. What is the velocity of the water as it leaves the pipe? V naught. What is V naught? And how far away from the pipe does it land? That's the displacement. Okay. So we would like to know what is V naught, how fast is the water moving when it leaves the pipe, and what is the total displacement? How far away from this broken pipe does the water land? I'm going to start filling in what I know in this chart. Right away, anytime I have my velocity at an angle, I break the velocity into components. So the velocity is V naught. It's making an angle of 30 degrees. So what I'm going to do right from the beginning of the problem always is break it into a horizontal and a vertical component. This component is V naught sine of 30. This component is V naught cosine of 30. I have to do this so that I can separate the velocity and be able to plug part of the velocity in for the vertical, this part, and part of it into the horizontal, this part. Okay, so I'm going to put the horizontal in, V naught cosine of 30, and I'm going to put the vertical in. The initial velocity is V naught sine of 30. In this problem, I'm using a coordinate system that calls right and up positive and left and down negative. Okay, other things I know in this problem. I know I'm going to call the highest point. That's going to be my end for this problem right now. I'm only going to look from right here. This is where it starts. To right here. This is where it ends. So I know the displacement vertically is 10 meters. The acceleration of gravity is negative 10 meters per second squared. And the final velocity at the highest point is 0. The water briefly vertically comes to a stop before falling back down. don't know the time, and we would like to find the displacement. Okay. So what equation can we use? Since I don't know the time, I recall that the third star equation doesn't have time in it. V squared equals V naught squared plus 2a displacements. The final velocity at this point here is 0. Plug that in right away. So 0 equals V naught sine of 30 squared plus 2g, sorry, this is not a variable problem, 2 times 10 meter per second squared times 10 meters. Just plugging in my acceleration and my displacement, 10 and 10. 0 equals V naught squared times the sine squared of 30 plus 200. The sine of 30 is 1/2, so negative 200 equals V naught squared times over 4, so 1/2 squared is 1/4. Multiply both sides by 4, I get 800 equals V naught squared. Taking the square root of 800, I get an initial velocity of 28.3 meter per second. So there's V naught. Okay, now we want to find what is the displacement. How far does it land? So to find how far away it lands, I need to know the time. Okay, so to find the time over here, remember these are the same. If I find the time over here, I know the time over here. So to find the time, I'm going to use the easiest star equation. V equals V naught plus AT, the first star equation. So time equals V minus V naught over A. The time equals the final velocity, which is 0, minus the initial velocity, which is 28.3 meter per second, divided by the acceleration, 10 meter per second squared. That gives me a time of 2.83 seconds. Now keep in mind that this time is only from here to here. If I want to know the total time, I have to double that. Okay, so the total time is twice that, or 5.66 seconds. That's the time I need to use here, 5.66 seconds. Displacement equals, I'm using constant motion because it's horizontal, velocity times time, which is 28.3 times the cosine of 30 times 5.66. And I get 138.6 meters. $100 meters. 138 meters. So we're talking about a football field here. Let me think. Does that seem reasonable? 28.3 meter per second. That's a pretty fast speed of the water. But I'm gonna just double check my math. Seems like a pretty far distance. Yep, this is what I get, 138.6 or 138.7 meters.